So it's exactly 9:20, so we start. So the first part of Chimie Générale is Atomistique. Then we're going to look at other subtopics of Atomistique, but principally we're going to study the atom and how it interacts with different atoms. It's all about atoms and their interaction with different atoms. So the first part of Atomistique will look at we're going to look at the model of the atom. The second part, we're going to look at the polyelectronic atoms. The third part will be the classification of the periodic table. And the last part will be the architecture of molecules. So like I was saying, so the first part will be the model of the atom. The second part will be the polyelectronic atoms. Then the third part will be the classification of the periodic table. And the last one will be the architecture of these molecules. So basically, atomistic, most of the times, the atomistic part is a bit historical. So most of the parts will be history, then some developments. But for you to really understand how things come about, you're supposed to, first of all, understand the history of the atom. So here's a question to you guys. So what is an atom? Mutale, what's an atom? What's an atom? Can you guys hear me? Can you guys get me?
Yes, it's the smallest particle of matter.
The smallest particle of matter. Mr. Kondwan, what's an atom? So everyone is going to give me the definition. After Kondwani comes Samuel, after Samuel comes Kennedy. So Kondwan, what's an atom?
You can say an atom is the smallest basic unit of a living thing.
Okay, Mr. Samuel, what's an atom?
According to me, I think an atom is a fundamental piece of matter that consists of neutrons, protons, and electrons.
Okay, Mr. Kennedy, what's an atom?
Okay, an atom is the smallest fundamental particle. Yeah, the smallest fundamental particle that makes up matter and cannot be split into any simpler thing or particle.
Okay, yeah. So everyone's definition of the atom is correct. So an atom is the smallest unit of matter. So we know that matter is made up of the three states: that's solid, liquid, gas. Then you also include the newly discovered one, which is called plasma. So now, from the definition that you've given me, people, before they came up with that definition, they use those principles, like you mentioned, matter, indivisibility, destructibility, for them to finally come up with a definition of what an atom is. So the first part of this coup will be basically the history of the atom. So the first part will be the history. Then today, in the second coup, the one that comes up at 15 to 17, we're going to look at the quantification of energy. Yeah, it's all about history. The first part is history, the model of the atom. I'm told you guys, for medicine and the laboratory pharmacy, you don't do calculations. It's all about just giving you notions about what happened and how people came about to understand the atom. Then later on, how we understand the atom in the modern world. So for you guys, there are no calculations, but for the engineering guys, there are calculations that are involved. Yeah. So the first person to decipher what the atom is and all about was a man called Aristotle. I think you guys know him. So he stated to say that basically atoms are made up of the three elements of can I say the earth, or yeah, of the earth, yeah. like if you guys have watched Avatar, they are what we call benders. They are those what we call earth benders, water benders, and fire benders. So he described an atom in terms of those three major states. So he started to say that atom is anything that is made up of or anything that can be a build up from fire, from water, and from the earth. But with later discoveries, you find people like Dalton come up with an atomic theory that explains different principles of the composition of matter. So now, before we even go as far as Dalton, we are here looking at what you call the periodic table of elements. You find out that the periodic table of elements is the table that simplifies or explains the states in which matter or an atom can be found in. Because on the periodic table, you have elements that are in the gaseous state, elements that are in the liquid state, elements that are in the solid state, depending at which temperature you are looking at them. So you can have standard temperature and pressure, that's 22.4 cubic decimeters, or you can have RTP, that's room temperature and pressure, 25 cubic decimeters. So matter is basically, I would say, matter is a synonym of the atom. So the atom and matter are basically the same thing because it is the atom that makes up matter. An example would be the human body. The human body is made up of different atoms, which are, for example, say the hands, the head, the legs, the toes, the ears, the hair. At the end of the day, the whole thing becomes a human body, and it is called matter because it is a result of small atoms. So an atom, in simpler terms, is the smallest unit that makes up matter. So, like I was saying, the first part of the atom was basically described in the four elements. That is, there are actually four, sorry. There's water, air, there's water, air, the earth, and fire. So he described the three elements of an atom to be found in these three states. So thereon we had the discovery of the atom by John Dalton in the year 1803. So he came up with a bit of generalizations about the atom. The first one was an atom is, like Kennedy stated, an atom is an indivisible particle, because the atom, like you guys said, is the smallest particle of matter. So it being the smallest, it means it also has a property of indivisibility. So with his further studies, he came to understand that matter is composed of indivisible, indestructible building blocks. So in other words, his definition of the atom was, because we know that matter is a polymer of the atom. I'm just using these interchange in these words, chemical words interchangeably. It's the same thing. Matter is a polymer, then the atom is the monomer. So matter is the polymer unit of the atom. So it is indivisible, indestructible, and the building blocks of this matter are those small particles that you cannot divide. Then furthermore, in the year 1803, he came up with a law called the law of multiple proportions, which in the new modern science, we sometimes call it the law of conservation of energy. In physics, when you talk about the law of conservation of energy, you explain it in the form of energy transformations from one state to the other, like kinetic energy to mechanical energy to gravitational potential energy. But with Dalton, because we are dealing with an atom, he explained it in the form of an atom. So the reactions that you're seeing here, the reactions that you're seeing here explain his principle. His principle is called the principle of multiple proportions. So, given for example, you have, I'll use this reaction here. It's the same thing. It's the same principle. It's the same. It's going to apply for both reactions. Given hydrogen and given chlorine, when 1 gram of hydrogen, 1 gram of hydrogen reacts with 1 gram of chlorine, it produces how many grams? It produces 2 grams of hydrogen chloride. Now, his principle is energy or the mass or the compositions of any particular element or atom in a reaction. It never changes. If you started with 1 gram of hydrogen and you started with another gram of chlorine, the sum of the two will be what you are going to find in the product. Now, there are situations where you are reacting, for example, say you have carbon here and you have oxygen here. Or let me use the combustion reaction. You guys know the combustion reaction, eh? When you react any organic compound with oxygen, you produce carbon dioxide and water. Now, for example, we take A. I won't have an example here, but I'll just assume this example. Eh? So take, for instance, you have A, which is methane, and B, oxygen. So when methane and oxygen react, they produce carbon dioxide and water. So you have 1 gram of methane and 1 gram of oxygen. The end products you're supposed to produce are supposed to be in a proportion of 1 to 1, or you're supposed to have a proportion of 2 grams in total, because his principle says that whatever you're going to react with reactants, you're supposed to produce a definite quantity with the product. So in this case, if I have 1 gram of methane and 1 gram of oxygen, I'm supposed to produce 2 grams of the product. Now it depends with their proportion. So if it's 2 grams, it might imply that I have exactly 1.5 grams of water. Then I also have 0.5 of carbon dioxide. Then the carbon dioxide can be lost. Now this is where now the principle comes in. Another principle that comes in. You have gases. Gases might be lost. So when you try to measure their mass, or maybe you want to calculate the quantity that you have, you might find the law that states that the proportions of given reactants is conserved in a reaction is not satisfied. Why? Because you have a gas that can be lost. So what I'm trying to say here is that every time you have a reaction of 2 reactants, A and B, the masses or the proportions that you start with are always conserved in a reaction. That is also known as the principle of multiple proportions. That is a definition that Dalton derived when he looked at the atom and how energy or proportions of masses are conserved in these atoms. Are there any questions? Are there any questions? So eventually he derived approximately 3 principles. That is, the first one, he says everything is composed of atoms, which are indivisible building blocks of matter. Secondly, he said all atoms of an element are identical, which is true. For a hydrogen atom, it is made up of hydrogen atoms only. For an oxygen atom, the oxygen atom is only made up of oxygen atoms. When you talk about relative abundance and relative isotopic masses, it's still the oxygen atom that we're looking at, but the difference is that the number of protons and the number of neutrons differ, but it's still an atom of oxygen. So the atom that we are studying here is still the same. It is still made up of the same particles. So his other generalization was all atoms of an element, an example is hydrogen, or any element on the periodic table, is purely made out of the same atom. They're identical. They're not different. They're identical. Then lastly, he said the atoms of different elements vary in the size or their masses, which is true. When you look at the periodic table, you find that atoms moving from elements moving from the left, which is hydrogen, to the right, where you have helium, the number of electrons increase and the number of neutrons also increase. Now, eventually, you have a difference or a variation in their masses. So we know that the mass of an atom is determined by the number of electrons, which can also be called the number of protons, because we understand to say that an atom is electrically neutral because the number of protons is equal to the number of electrons. But in a case where the number of electrons differ, you have what you call an ion. So we understand that the number of protons and the number of neutrons are the same, number of electrons are the same. So the mass of atoms vary in that order. So as the number of neutrons and protons increase, it means there is a variation between two different elements. Take, for instance, oxygen with at exactly 8 neutrons and 8 protons with 8 electrons. With in its atomic state, it has 8, 8, 8. Then you have an element like phosphorus, which has exactly 31 gram per mole. That's the number of neutrons plus the number of protons. So 15, which is the number of electrons, minus 31 gives you, is that 15? 16. So you have 16 neutrons and 15 protons and 15 electrons. So you see that variation. As the number of neutrons and protons increase, the masses of these atoms also increase. So someone just came in. I'll just give a recap. So we are saying the atom is the smallest particle of matter, or in other words, we are saying matter is the polymer and the atom is the monomer. So we have different people that described the atom in different ways, because before the definition of what an atom really is, people had general ideas about what the atom was. So the first one was Aristotle, that he described the atom in 4 principal elements. He defined an atom in terms of water, the earth, fire, and air. So like I gave an example to say, those people that watch the Avatar, these are the four elements that you always look at: water, air, the earth, and fire. And they're called benders. So you have fire benders, water benders, etc. Then after Aristotle's discovery, or maybe say generalization, we have people like John Dalton that explains the atom in form of matter, which is composed of indivisible and indestructible building blocks. Then further on, I started to say that he also came up with another law that can also be called the law of energy conservation in chemistry. It can also be called a law of energy conservation. Why? Because given, for example, you have this reaction here, hydrogen plus chlorine gives hydrogen chloride. You start with a gram of hydrogen and another gram of chlorine, you are going to get exactly the same proportion. That is 1 gram plus 1 gram is equals to 2 grams. Now, it depends with the reaction you're looking at. So I gave an example of the combustion reaction. So we understand that any organic compound that reacts with oxygen gives hydrogen, or hydrogen dioxide, which is water, and what's this? It's dihydrogen oxide, not hydrogen dioxide. It's dihydrogen oxide, which is water, and carbon dioxide. Now, we are saying the law of proportion will always be maintained. It will never change. But in certain cases, it might change because of certain factors. Take, for instance, like I said, you have an organic compound, methane, reacting with oxygen. You're going to have carbon dioxide and water, dihydrogen oxide. So because we know that carbon dioxide is a gas, you find that the gas might escape and might not abide the principle of multiple proportions. So there are cases where you have a reaction and you have gases that are produced. So because that's a gas and you have no control, we chemists have no control over gases. So you might find the gas has escaped. You find that the law of multiple proportions is not well observed, but in the actual sense, it is observed, but you have a gas in the products. So because you have a gas in the products, the gas, we have no control over it. The gas will surely escape. But take note, the law of multiple proportions will always be satisfied, because whatever you started with is whatever you end with. Are there any questions so far? Then before I allow a question, we concluded to say John Dalton's theory, atomic theory, had three general principles. The first one was saying everything is composed of atoms, which are indivisible building blocks of matter. And the second one was all atoms of an element are identical. And the last one was atoms of different elements vary in size and mass. Are there any questions? Okay, so furthermore, we had another famous scientist by the name of J.J. Thomson. So J.J. Thomson's discovery was basically the discovery of what you guys call the electron. So what he did was he established to say that the atom has a positively charged part, and because it has a positive part, it's automatic. If you have something that is positive, when you're looking at charges, if you have something that is positive, it's automatic that there is supposed to be an opposite charge. So in this case, in 1897, Crookes cathode ray, I think you guys know what the Crookes cathode ray is. So with the Crookes cathode ray, J.J. Thomson demonstrated that cathode rays are actually made up of negative charges. So after finding out that the electrons, or maybe say the cathode rays are made up of negative charges, he assumed that the atom or the cathode rays have an opposing charge, because when you go to electromagnetic or via electrostatic, you find out that in every given charge, in every positive charge that you have, you always have a counter charge, because you see, atoms in real life always want to attain neutrality. That's the whole building block of chemistry. Atoms always want a state of neutrality. So if you have a negative charge, it automatically means that you are going to have a positive charge. So J.J. Thomson, in the year 1904, he finally discovered to say that a substance that can be called an atom has a negatively charged particle. Now, because it has a negative charge, it's automatic that it's going to have a positive charge. Now, for him, he just ended there. But with further discoveries, like we're going to look at when we talk about the quantification of energy, Niels Bohr, with him, he discovered and stated that you have what you call stationary energy levels. So in these stationary energy levels, this is where you find electrons. Yeah, like you guys know, like electrons are found in orbitals. So it was because of such discoveries that each one had to contribute. So J.J. Thomson just said, no, the atom has a negative charge. So with common sense, it is automatic that because you have a negative charge, you are going to have another opposing charge, which is the positive charge. Is there any questions? Okay, so for Jahed, then we also have another famous scientist by the name of Ernest Rutherford. So Ernest Rutherford used the helium radiation. Now, here's a question. Helium, which type of radiation is this? Is it gamma, beta, alpha? The question here. Is it helium? Is it an alpha, gamma, or beta radiation?
An alpha.
So if it's an alpha radiation, does it penetrate through particles? Does it penetrate through particles? I'm saying, does the alpha particle penetrate through other particles? Or the alpha radiation, does it penetrate through other particles? Okay, it's like never radiation, non-radioactivity. So an alpha particle does not penetrate unless it's a vacuum. But when it is when it encounters a particle, it deflects. So with the same principle that I have stated, Ernest Rutherford in the 1913s, he used the helium radiation to what's this? He projected the helium radiation in a metal of ore. What's ore? This is French. Ore. What is it?
Gold.
Yeah, exactly. So he used the helium radiation and he subjected the helium, the metal gold to a radiation. That's an alpha radiation. So at the end of it all, now, this is a diagram that explains what happens when you have an alpha particle and the alpha particle is subjected to a material. So wherever you have got two mass spaces, like I said, whenever you have a vacuum or spaces, the alpha particle penetrates and goes to the other side. But when you have an alpha particle interacting with another particle, when an alpha particle interacts with another particle, the alpha particle is deflected. So it was found that when he subjected the metal to the alpha radiation, it hit, or it was deflected. The nucleus of the atom was the one that deflected the radiation. So after him subjecting this metal to a radiation, that's alpha radiation, he found that the nucleus and the alpha particle had interacted. Now, because the nucleus of an atom is made up of protons and neutrons, it is a bit denser and it is a bit of substance. So because of that principle, the alpha particle had to deflect. Then because of that, he said and stated to say, no, because there is a deflection of the alpha radiation, this means there must be something in the center of the atom that helps or that necessitates this type of deflection, because it does not happen for electrons. Electrons, the alpha particles cannot penetrate, because even electrons, when this is a question we're going to answer when you look at the compositions of an atom. Why is it that the electron mass is never added to the normal mass of an atom? It is because we understand that the mass of an electron is nearly equals to 0, which is 9.1 times 10 to the power negative 31 kgs. It is nearly equals to 0. It is for this reason why we do not add the mass of an electron to the mass of the atom. We only use the protons and the neutrons. So when you look at this diagram here, when it's coming across to my electrons, this to my red with my more, it shows that the particle is passing or penetrating through the electron. It is because of the same principle. the electron is nearly negligible. But for the mass, or for the noyau, which is made up of both the positive and a neutral charge, it's a big particle, or maybe it's of great quantity, that when an alpha particle is subjected to the nucleus, it is deflected. So all in all, Ernest Rutherford was the one that led to the discovery of what you guys now call the noyau, or bien the nucleus. Are there any questions so far? Okay, so now
The part you were saying, the alpha particles are like the electrons, and when the rays were passing through there, they were not deflected because my network was reconnecting.
okay. So I was saying, so if you have a network problem, please state so that I wait for you to reconnect, then we forge ahead. So I was saying the atom is made up of positive and negative particles, and we know that it's made up of a nucleus. So when the alpha particle, now with the discovery of the electron, people knew that, okay, there is an electron somewhere. So, and because we have an electron, we automatically have a proton, the positive charge. So now Ernest Rutherford carried out an experience, say, okay, we have a metal, and a metal is matter. It is made up of atoms. That is, in accordance to John Dalton's law, or generalization. He states that all atoms of an element are identical. It means, so in this gold plate we have here, we have small atoms, and the small atoms of gold are identical. At the end of the day, because they are identical, they form a very big plate of the metal, or the element gold. So when the metal was subjected to an electron radiation, an alpha radiation, it was found that the nucleus of the atom, the nucleus of an atom, having like, I don't have a good word for this, but because the nucleus of an atom is way denser than the electron, it was found that the alpha particle repelled or was deflected by the nucleus. But in regards with the electron, you find that the electron, like I said, we do not consider the mass of an electron. I said the mass of an electron is 9.1 times 10 to the power negative 31 kg. So we do not consider the mass of an electron when calculating the mass of an atom. It's because of the same reason, because it's nearly equals to 0, or it's negligible. So now we're saying, when the alpha particle is subjected to the electron, because is equally nothing, the alpha particle penetrates. But because the mass of an atom is made up of the nucleus being a part of the atom that has substance, or maybe say is a quantifiable part of the atom, the alpha particle was deflected. Is it clear? The alpha particle was deflected. Then therefore, now that led to the discovery of the noyau. That led to the discovery of the noyau, which is also known as the nucleus. So is it clear, Mutale?
Yes, it is.
Okay. Are there any questions? Are there any questions? You're welcome. Are there any questions? Okay. It's like history, it's all about history. Don't worry. You guys, the part that you start doing to my bit of calculations is Kuntanj. So then we have two important discoveries. So I'll start with Albert Einstein's discovery. Then I'll go to Boyle's. Then I'll go to, who's this? Erwin Schrödinger. Yeah. So with Albert Einstein in the year is it 1915? 1915, discovered the formula, the famous formula, which is E is equals to the mass multiplied by the speed of light. Okay, even though that formula has got two paths where it comes from, the other part is special relativity, and the other part is the photoelectric effect. I'm not going to go much in detail, but yeah, this is where the two come from. So Albert Einstein's discovery of the photon, you guys know what a photon is, eh? A photon is a particle, or maybe say a measurement of a radiation. Like I would say, when you go to the hospital, you go on the balance. When you go on the balance, they measure your mass, not weight. They measure your mass. So that quantity of your body that they are measuring has a unit kg. So it's the same thing. The photon is like a unit for radiation. So radiations might differ. You have got electromagnetic radiations, and you have from that radiation you have microwave radiation, you have infrared, you have there are a lot. You guys have done this before. Yeah, there are a lot. So a photon is basically a unit. Sorry for the. Can you guys see now? Can you guys see? So my network had cut myself.
Yeah, yes, you can see.
Can you guys see?
Yes.
Okay. As you guys just respond that, so that I also become a bit fast to start explaining. Yeah. So we are saying a photon is a measurement used for a type of radiation. So with the discovery of the photon, people now, like, the first part of photon was done by a man called Maxwell Planck. I think you guys know him. Then further discoveries with Albert Einstein and Maxwell Planck working together, they had now discovered what you guys call the energy formula, which is mass multiplied by the speed of light squared. Then later on, Albert Einstein did the same experiment. Now the same experiment here he did was, now he used another metal. It's the same experiment like Rutherford's experiment, but for him, he was just trying to really define what happens when an atom is subjected to a radiation. So it was found that given an atom, and when you subject it to a type of radiation, an atom on its own has got a certain type of energy. So when it is subjected to a radiation, there is an energy that is supposed to be overcome. Is it overcome? Like
it's 10 o'clock.
Like activation energy. There's an energy that you're supposed to overcome for you to eject a photon. So with Albert Einstein, he used the same principle here, the God principle, where you have a metal plate and you're subjecting this metal plate to a radiation. So because we understand that a metal plate or any atom has at least an amount of energy. So when the energy of the metal plate is higher than the energy of the radiation, it means no photon is going to be produced. No photon will be produced. It's the same principle. When you have a reaction and the activation energy is it lower? If a reaction cannot overcome the activation energy, it means that reaction cannot take place, because for a reaction to take place, you need it to overcome the activation energy. It's the same principle. If the energy of the radiation is less than the energy of the metal, it means you're not going to have a ejection or maybe the emission of a photon. But if the energy of the radiation is greater than the energy of the metal, you are going to have a photon that's going to be produced. You have radiations that are going to be produced, of course. Then the photon, like photons are like a background radiation. Like they are after like work, when you're doing work, there's what you call friction. The friction results in heat energy, and that is called energy loss. It's the same principle. So photons are like the heat that these metal plates or these atoms get. So radiation is in another form that we call photons. So irradiation can result into the formation of a photon. So like I said, a photon is basically a unit used to measure radiation. Yeah. So Albert Einstein's principle, that's the photoelectric effect, he subjected an atom, or for example, we're going to take this metal plate, to a radiation. So we are saying if the energy of the radiation, which is here, for example, we have an alpha particle, if the radiation here is greater than the energy of the metal, it means there is going to be a photon that's going to be produced. If the energy of, take note, if the energy of the radiation is greater than the energy of the metal, because we know that each metal possesses at least an amount of energy. If the energy of the radiation is greater than that of,
I need to record something, so I don't know if you can just kindly repeat some, maybe some seconds ago.
Okay, so I'm saying we understand to say that an atom has got at least an amount of energy, and we are subjecting this atom, or bien this element, to an electron or to an alpha radiation. So we are saying if the radiation of this, say for example it's alpha, is greater than that greater than the energy that this atom possesses, it means we're going to have we're going to have a photon that's going to be produced. Yeah, photon is like the energy loss side. Photon is like the energy loss. So we're going to have radiations that are going to be produced. Then photons will also be produced because they are like every time you are trying to, because when we talk about Boyle, we are ejecting electrons. So every time you are subjecting this atom to this radiation, there are other radiations that are going to be coming out. Like the same principle here. Some will be going past through, some will be deflected. Then some will be lost as energy. Those ones that are lost as energy are what you are calling photons. That's what we are calling photons. Then we say that if the energy of the metal, because we are saying an atom can be metal, it can be anything. So because it's what defines matter. So if the energy, we know that the energy, an atom at least has a minimal energy that it has in its nucleus. So we are saying if the energy of the atom is greater than the energy of the radiation, it means you are not going to have any photons that will be produced. Now I gave an example of a reaction, a chemical reaction. So for a reaction to take place, you need activation energy. Now, if the activation energy of a reaction cannot be overcome, so it means you're not going to have a reaction. But the principle basically for any reaction is the reactants are supposed to, or they must overcome the activation energy for them to produce products. It's the same principle. So if the energy in the metal is greater than the energy of the radiation, it means you're not going to have any photons produced. Then if the energy of the radiation is greater than the energy of the metal, it means you are going to have a photon, or radiations are going to be produced. Is that clear? You guys have no formula, so just brief history. Any questions? Okay, then we come to Niels Bohr. So Niels Bohr, we're going to look at it in detail when we talk about quantification of energy. But for now, we're going to just go direct to Erwin Schrödinger. So Erwin Schrödinger, now, this is where we talk about probability densities and electrons. So this is where I also talk about what we talked about in those that are attending organic chemistry. We talked about quantum entanglement and quantum superposition. So because he explains electrons' positions to be found in probability densities, he came up with the two principles that I stated last time. That's quantum entanglement and quantum superposition, which is quantum superposition, the state of an electron being in two positions at the same time. Then quantum entanglement, which is an effect done to an electron in one state affects the other in another state. So basically, Erwin Schrödinger defined to say the atom is made up of a positive charge, yes, which is called the nucleus. The nucleus, you guys know that it's positively charged, and is also made up of orbitals. Now, Niels Bohr defined orbitals to be just stationary lines, just stationary lines. We're going to look at that later on. He just described energy levels to be just straight lines. Like you guys know, these to my things you like drawing. No, to my seko, shan, shan. Something like this. Something like this. This is Niels Bohr's discovery. So this is how he discovered the atom. He was like, no, this is how the atom is supposed to be. Now, Erwin Schrödinger comes in with the principle of quantum superposition and quantum entanglement, stating that the electron is found at whatever position you are looking at. So there is what you call another principle. It's just an analogy of what quantum superposition is. So he said, take for instance, you have a cat, and we take that cat in a box. We put the cat in a box. Then we put maybe say radium. You know what radium is? Please respond. You know what? If you don't know what it is, you say I don't know. Then I explain. You know what radium is?
Yes.
Yeah.
No.
So okay, there are those that know, those that don't know. So those that know, what is radium?
Some radioactive substance.
Exactly. So radium is a radioactive substance. So when you subject any living thing to a radioactive substance, we know it's radioactive. It's mutated radioactively. So this is what happens. Now, Erwin Schrödinger explains quantum superposition in this way. You get a cat and you put it in a box. Then you also put a radium source of radiation there. So what is going to happen? What is going to happen? This is nothing to do with chemistry, it's just logic. What is going to happen? If you put a cat in a box and you also put radium, or maybe take for instance, we put you in a house and we also put a radium radiation there. What is going to happen? Common sense first. I need a response.
You die.
Exactly, you die. So now his principle states that we are saying quantum superposition is the ability of an electron to be found in two states at the same time. Now, couldn't say is you die, but I can also say you won't die because we do not know your state. You see, maybe we do not know your state because maybe the radium that we used had expired. You see, or maybe the person that was labeling, the person that was responsible for labeling the atoms had labeled sodium as radium. So you find that sodium cannot react with a person. It can't kill you, or with a cat, it can't kill you. So the principle of quantum superposition is the state of an electron being in two positions. So me, or maybe the cat in the box, if you put the cat in the box and you put a radium radiation, you are at no will to say that the cat is going to die, because you do not know if the cat is going to die. It's only going to die when you measure the system. What I mean by measuring the system is you observing what happens. So when you go there, check in the box and find the cat is dead, you are now going to say, okay, the cat is dead. If you go there and check that the cat is still alive, you are supposed to say the cat is still alive. So it's the same principle. An electron with Erwin Schrödinger, no, this is Erwin Schrödinger now explaining the atom in form of a quantum mechanics. So he says an electron is found in any position, for as long as you measure the system, for as long as you check where it is. So we can't say the electron is found in energy level 1, we can't say the electron is found in energy level 2, but we can only say the electron is in a state of quantum superposition. We can only know its state when we measure the system. So when we measure the system, now measuring is the same principle that I used of a cat. You can only find out the state of the cat if you check. If the cat is dead, you state that the cat is dead. If the cat is alive, you state that the cat is alive. So all in all, what I'm trying to say is an electron will always be found in any position, So it's up to you to measure or find out where that position is. So now, with further discoveries, you guys, I'm not supposed to exhaust you with a lot of information, but with the engineering guys, we go as far as explaining the principle of uncertainty. There's what you call Heisenberg's principle of uncertainty. So Heisenberg's principle of uncertainty states that you have a particle with position x and the momentum p. So you understand momentum is mass multiplied by, velocity? So the mass multiplied by the velocity of a particle is momentum. So you have a plane moving. This is another example. You have a plane moving. So normally, you are not supposed to measure. That's normal logic as well. You can never know the position of the plane and know the momentum of the plane at the same time. It's not possible. You have to know one and let go of the other. Just like the Bible states, you are not supposed to serve two masters at once. You love the other and hate the other. It's the same principle. You are not supposed to know the state of one and also know the state of the other. It doesn't work that way. You know the momentum of the plane. You forget. In other words, you forget about its position. You note its position and you forget about its momentum. I know it's a little bit that Apakamaning. Is there any questions? I will re-explain if there are questions. Are there any questions? Okay, so we go forge ahead. Then now this is just another diagram that shows how the atom was discovered, from the Greek to Dalton to J.J. Thomson, Rutherford, Niels Bohr. We're going to look at him later, and Erwin Schrödinger. Yeah. So now the atom. The structure of the atom is made up of the nucleus and the electron. So we are saying the nucleus is positively charged and is made up of neutrons and protons, and the orbitals are made up of electrons, which surround the nucleus. So we are saying the noyau, bien noyau sphérique centré, noyau de la ordre, that is 10 to the power negative 15 meters. Then la taille de l'ensemble de l'atome de la ordre. So this is just like the size of the radius with reference to the noyau, which is 10 to the power negative 15. And the size, I don't know, I think there's something missing here. Yeah, but the size of everything together, that's the atom, is should be 10 to the power negative 10 meters, I think so. This should be 10 to the power negative 10 meters. So we are saying the nuclear notation of an atom, nuclear notation, you guys know what nuclear notation is. So the representation of an atom on the periodic table is what you call nuclear notation. So an atom is made up of the symbol, that's on the periodic table, is the symbol X. The A here represents the nombre, the nucleon, which is the number of protons and the number of neutrons, which is also known as the mass of the atom. Then Z, which is the atomic number, which also signifies the number of protons, which also signifies the number of electrons. Now, it only signifies the number of protons and the number of electrons when it is neutral. When it is unbalanced, it now forms what you guys call an ion. So an ion is a charged particle that can either be negative or positive. So an ion is a negative or charged particle So an ion is a result of an imbalanced electron-proton distribution. Are there any questions? Okay, we'll forge ahead. So we are saying the properties of the elemental particles, that is the electron, the proton, and the neutron, have the following charges. So in the normal chemistry, we're doing Zambia, we were saying the electron here has a charge of -1, the proton has a charge of +1, and the neutron has a charge of 0. It's the same now, but here those charges we're showing are just unit charges. So now the actual charge that the electron has is -1.6 times 10 to the power -19 coulombs, and that of the proton is +1.6 times 10 to the power -19 coulombs. So if there is need to note this constant, please take note. Then the mass of an electron, I remember the mass of an electron was 1/1840 unit atomic mass, but now the mass of an electron is 0.9, or bien 9 times 10 to the power -31 kgs, or bien 0.9 times 10 to the power -29 grams. Same applies to the proton. So the proton is 1.7 times 10 to the power -24 kgs, and the mass of the neutron is 1.7 times 10 to the power -24 grams. So in kgs, this becomes 1.7 times 10 to the power -27 kgs, and 1.7 times 10 to the power -27 kgs. So in other words, this now concludes to say that the atom is made up of three principal particles. That is the electron, the proton, and the neutron. But all in all, we find that the mass of an atom is made up of the neutron and the proton. Now, the question I asked last time was, now why don't we add the mass of an electron? The mass of an electron, like you can see here, even without the powers, this is 0.9. Now, if you round it off here, it's equals to 1. Now, if you round this one off, it's equals to 2, equals to 2. So automatically, this one here is a bit less than these two combined. So it is for this reason why we say the mass of an electron is never included. Oh, sorry, yeah, the mass of an electron is never included in the unit mass of an atom because it is negligible. It is negligible. So we are saying an atom possesses Z protons and also has Z electrons. This is what defines an atom's neutrality. So an atom is electrically neutral because a number of electrons is equal to the number of protons, except when there is an imbalance, which results in the formation of what you call it? Is it an ion? Yeah. So it forms a cation for the positive, for the metals, and an anion for the non-metals. Then you're also saying the presence of the neutron assures the cohesion of the noyon. So it is because you have neutrons in the noyon that you have a cohesion force between the electrons and the protons. So it's like the neutrons are what keep the protons contact, and they also contribute to what you call a nuclear charge between the electron and the proton. Then furthermore, we are saying the mass of an atom is equals to A, which is in mass atomic unit, and the mass of a mole, which is the same as that of A in gram per mole. So I explained this when we look at the carbon atom and its relative isotopic masses and how they are derived. Any questions so far? Okay, we forge ahead. So this is just another nuclear notation. So we are saying the A represents the mass and the Z represents the charge, or bien the number of protons, or bien the number of electrons when it is neutral. So when we are calculating the number of neutrons, so we are going to say the formula is A, which is the mass of the atom, is equals to Z, which is the charge, the number of electrons, the number of protons, or bien the number of protons, plus the neutrons will give the mass. So if you're calculating the number of neutrons, simple mathematics, you are going to move the Z on the other side, and you're going to have N is equals to A minus Z. So you're going to have a number of neutrons. So for example, carbon number 6 with atomic mass 12, the number of electrons is 6. The number of protons is also 6, which is here. Number of electrons is equal to number of protons. Then the number of neutrons will be the mass, which is 12, minus Z, which is 6. So 6 from 12, that's going to be 6. So it's going to be 6 electrons, 6 neutrons, 6 protons. Yeah, but this differs now when you talk about the principle of isotopes. So now here, this is just another explanation about ions. Ions are formed when there is an imbalance of electrons. So the number of protons and the number of electrons differ. That results in the formation of an ion. So there are positive charged ions and the negatively charged ions. So the positive are called cations and the negative are called anions. So positive charged particles that are that is metals are called cations, and they lose electrons. So the result, another definition of an ion is it's a charged particle that is caused, or an atom that is made or formulated as a result of loss or gain of electrons. So when you have loss of electrons, you have what you call a cation, and when you have gain of electrons, you have what you call an anion. Then we have now what you call isotopes. So an isotope is any atom having the same number of protons, same number of neutrons. Is it same number of neutrons? What's the definition of an isotope? So an isotope differs in the number of, in the mass, and when you compare the mass to the number of, is it protons? So that's the difference. The isotope differs in the number of protons that you have and the number of neutrons and protons together. That's the mass. So in other words, it differs with a Z, nombre, ou bien numéro atomique Z, et le nombre de masse. So an isotope, these are atoms of the same element having the same atomic number, or bien number of protons, but it differs in the mass. So now here, because if I use protons, it's going to confuse you because the protons again are going to add up for the mass. So here, when we say numero atomic, we're going to consider this to be the number of electrons, so that we just make a difference between the number atomic Z, which is also the number of electrons, or bien the number of protons, and number, the mass, which is the mass of an atom made up of the neutrons and the protons. So we have different isotopes. We have carbon 12, carbon 13, carbon 14, and they also have different uses. One is used for radioactive dating and etc. Others are used for therapy. Others are used for what else? Yeah, forgotten that. But some are used for detecting leakages in different chemical industries. Yeah. Then you have hydrogen with three isotopes. You have hydrogen 1 with only one noyon. That's one neutron. One neutron. Then you have one electron. Then deuterium with one neutron, with one proton, with one electron. Then we have tritium with 2 electrons, 1 neutron, and 1 electron. So now we go to relative atomic masses. So we understand to say that because of the variation of masses, or bien because of the discovery of isotopes, masses differ because we are always looking at what's relative to the other. We're going to explain that when we talk about the carbon atom. So because we have masses that are relative to each other, we are supposed to calculate their relative masses, in the sense that you have, for example, an exam. Take, for instance, this is an exam, the French exam. In your first control, you have a 12. In your second control, you have a 13. In the third control, you have a 14. Now, for us to get your relative moyenne, we are supposed to get the average of the three. Then at the end of the day, we are going to say, okay, this person got a moyenne of, is it 13 point something? When you do the average of the three, you get something like 13 point something. So that's the same principle here. Because atoms or bien elements in nature exist as different isotopes. It is for this reason why we are supposed to calculate their relative abundances as they occur in nature. So the carbon-12 atom has a relative or bien percentage isotopic, which is 99%. Then the carbon-13 has 1%. Then the carbon-14 has traces, which is almost like nothing. Now, for you to get the relative isotopic mass, we are going to say, please follow me with the calculations. 99% times 12. 99% times 12. 99% can also be written as 99 over 100 multiplied by the mass of the atom. So that's 99% multiplied by the mass of the atom plus 1% multiplied by 13, that's the mass of the atom, plus 0 multiplied by 14, which is the mass of the atom. Then we find out that it gives us exactly 12.01. Now, it is for this reason why the carbon atom is used as a reference for unit atomic masses. Okay, I know my calculations are permissible. So I repeat. So we are saying the mass of the carbon-12 atom is 12. It's a mass atomic. It's 12 grams per mole. That of carbon-13 is 13 grams per mole. That of carbon-14 is 14 grams per mole. Now we are saying their percentage or their relative isotopic masses or percentages in nature are equivalent to 99%. So we are saying the carbon-12 has a percentage in nature that is 99%. 99% of the carbon, every time every time you're looking for carbon, you find 99% of carbon-12 with a mass of 12. Then there's 1% of carbon-13, and there is equals to nothing, like there's nothing at all for carbon-14. So we are saying for us to get the relative atomic masses, we are supposed to make a moyenne of everything. Like I said, in your example I gave controls, you have 13, you have 12, and you have 14. For us to get your average results, we are supposed to make a moyenne for everything. Then later on, we're going to have a result. That is 12 plus 13. That is it how many? 12 plus this is going to give you, is it 25? 25 plus 14 will give you 39. 39 divided by 3. Okay, we'll just take it 40. 40 divided by 3 will give you something like, is it 13 point something? Somewhere there. So your moyenne for everything now will be like 13.94, for example, it'll be like 13.94. Now, the same principle here will be used now to calculate relative atomic masses. Now we are saying the mass of carbon-12 is 99% in nature. So it will be 99%. 99% can also mean 99 over 100. 99 over 100 multiplied by 12. This 12 is this one here, or beyond this one here. So in other words, what we're doing is we're saying 12 multiplied by 99 plus 13 multiplied by 1 plus 14 multiplied by 0. This is what we're doing here. We're saying 99% will be 99 over 100 multiplied by 12 plus 1 over 100 multiplied by 13 plus 0 multiplied by 14. So we get exactly 12.01. That's what you get. You guys have calculators so that you also follow along with the calculations. So now this is why I said it is for this reason why the carbon-12 atom is used as reference when we come to atomic mass units. So we are saying one atomic mass unit is equivalent to 1/12 of the carbon atom. So is it clear with the calculations here? So the same we are going to do for carbon, chlorine 35 and 37. So chlorine 35 has got a percentage, that's percentage isotopic, over 75%. Then the other one has a percentage isotopic over 25%. So when you add the two, it's supposed to give you 100. So the same principle is 75% multiplied by 35, the mass, plus 25% multiplied by 37%. Or in other words, the formula is whenever you're calculating the mass, of what is it? See, whenever you're calculating the mass of relative mass of an atom, you are supposed to consider x being the percentage of the isotope multiplied by its mass. So the percentage of the isotope multiplied by its mass. That is going to give you the relative atomic masses, which is what we are doing here. We're saying the percentage multiplied by the mass plus the percentage multiplied by the mass. It's going to give us exactly 12.01. Now, the periodic table varies. Some periodic tables, like the ones we're using in Zambia, the periodic table we're using in Zambia had whole numbers, but we're going to use, I'll use the same one with whole numbers, just clarify on a point, where there's a point where, this used to be a question where they used to ask us about why the chlorine has a mass of 35.5. Now we're saying because it is an isotope. Okay, yeah, in one way that was the correct answer, but it's also wrong because all elements of the periodic table are actually isotopes of themselves. So when you look at this periodic table here, you find that when you look at this one, these ones are the correct calculations of all the elements. Now you have everything with my points here. Now this shows that everything now on the periodic table is actually an isotope, not what we were saying in Zambia. No, chlorine is the isotope on the periodic table. It was correct here in the chemistry, G11, G10, G12, but it is wrong now. It is wrong because all elements on the periodic table are actually isotopes of themselves. You can see from the variations of the masses here. You have helium with 4.0, you have neon with 20.18, we have argon with 39.95, we have beryllium with 9.01. So it's a variation. So the masses are a result of this relative abundance that we are talking about here. Are there any questions with this? Okay, we forge ahead. Today it's like everything is clear. What happened over the weekend? What happened over the weekend? It's good. It's good that everyone is following. So let's hope it will be the same thing for organic chemistry. Yeah. So we are okay. So we are saying the hydrogen atom has got three isotopes. That's protium, deuterium, and tritium. You guys know this one, so I won't hassle too much about this. Yeah. So we have les autres exemples des isotopes. So this is what you have. You have magnesium 24, 25, 26, 12, that's carbon 12, carbon 13, carbon 14, oxygen 16, oxygen 17, oxygen 18. So from today onwards, please, from today onwards, it's not that chlorine is the only isotope on the periodic table. No, all elements of the periodic table are isotopes. All elements on the periodic table are isotopes. So that answer we were given in grade 10, in grade 11, in grade 12 was because the periodic table we're using as reference. Every time we're using that periodic table, we're considering the mass of chlorine to be equal to 35.5. And it was the only one with a decimal. And it's for this reason why we're saying it's an isotope. But
can you repeat? My network was reconnecting and it was saying a known error happened from
okay.
where you were talking about the how they found that carbon is 12. Sorry,
no,
about 12.01 grams per
I've
mole.
not even, okay, I've not even gone to the relative mass units. Okay, I'll still repeat. The idea is you guys are supposed to understand before going to school. We are supposed to understand why certain principles are like that. So we are saying the mass of the carbon atom is 12. We're saying the mass of the carbon atom is 12. The mass of the carbon 13 atom is 13, and the mass of the carbon 14 atom is 14. So we're saying, for example, these were results for the French exam or bien at the faculty. So for 3 modules, that's analyse, algebra, and mécanique du point. So now for us to get the average for everything, we are supposed to now get the average is also known as the moyenne. So we're supposed to get the moyenne of the 3. Then later on, we are going to use that as a reference, because you guys, when you do statistics, you understand that the moyenne is the center of tendency in statistic distribution. You have what you call a cut de la moyenne. I won't go in detail about that, but the idea is you have a moyenne. The moyenne shows the central tendency of data distribution. So in this case, we have 12, 13, and 14. Now, our moyenne might be equals to something like 13.94. I'm just assuming, right? When you add the 3, it might be equals to 13.94. Now, we are saying for us to get the question. Is the question? Okay. So we are saying for us to get the relative mass, the formula is the mass ou bien the percentage isotopique fois times, which is 4 is times. So 99% times 12 plus 1% times 13 plus 14 or 0% times 14, which will give 12.01. So we are saying 99 over 100 is the same as 99% times 12 plus 1% times 13 plus 0% times 14. Then we're going to have 12. Now, this is why I came up with a point saying, it is for this reason why the carbon-12 atom is used as reference for calculating unit atomic masses. So I said 1 unit atomic mass is equivalent to 1/12 of the carbon atom. So we're going to look at that. It's the next part. So 1 unit atomic mass. Eh? You have a question?
Oh, I'm sorry. I was trying to understand, like, what you mean, like 1/12. You mean 1/12?
Yeah, 1/12, as in, what's 12 divided by 12? It's 1 day.
Oui.
Yeah, 1. So it means 1/12 of any atom. Like, okay, let me, when I get there, I'll explain it. I'll use a diagram to explain what I mean. But is it clear here? I'm not, that's the next part I'm going to. Is it clear here?
Yes, it is.
Okay, yeah, that's where I'm going. So then we have what you call isotones, même nombre de neutrons, isobar, même nombre de nucléons, isoelectronic, même nombre des électrons. Then we have now the definition I'm talking about, Mutale, is this one now. So we're saying the structure of the atom is made up of the mass. Now the mass is the sum of the neutrons, or sum of electrons, even though it's negligible, plus the mass of the protons plus the number of neutrons gives us the mass of the atom, atomic mass. So now we are saying 1 unit atomic mass, 1 atomic mass unit is equivalent to 1/12 of the carbon atom. So we are saying, what is the mass for carbon? The mass for carbon is 12. So what is 1/12 of the 12 of, sorry, what's 1/12 of carbon 12? Now use the mass. What is 1/12 of 12?
It's just 1.
Exactly. So it is for this reason why we are saying, yeah, exactly, it's 1. So it is for this reason why we are saying 1 atomic mass is equivalent to 1/12 of the carbon atom. 1/12, that's 1/12 times 12. That is equals to 1 atomic mass unit. So now, in other words, what it means is, for every atom that you have, the number of units that you have in that atom is equivalent to its relative mass. So what I'm trying to say is 1 atomic mass unit for chlorine will be 1/35.5. So we're saying 1 atomic mass unit for chlorine, for the chlorine atom, is equals to 35.5 of the chlorine atom. So in other words, 1 atomic mass unit is equivalent to 1/12th or bien 1/nth of any atom. 1/nth of any atom. So this is the formula that you have here. Where is it? Yeah, this one here. So we are saying 1 atomic mass unit is equals to 1/nth of any atom that you have. And here another justification would be the relative mass of any atom is derived from the nucleus. So now how do we define that? We are saying 1 mass atomic is equals to 1/Avogadro's constant, which is 6.02 times 10 to the power negative 23. So we're saying 1/Avogadro's constant will give us an exactly, that's exactly 1.66 times 10 to the power negative 24. Now, this number that we have here shows that definitely the mass of an atom is made up of, these numbers. It's made up of this. So because of that generalization, we now say, okay, in other words, 1 atomic mass unit is equals to 1/Avogadro's constant, or it is also equals to 1/n element, any element. To n here will stand for n element or bien Avogadro's constant. Now when it stands for Avogadro's constant, it's a justification about what we consider when getting the mass of an atom. Then it can also stand in for any element, because we are saying if it's a condition, if 1 atomic mass unit is equals to 1/12th of the carbon atom, it implies that 1 atomic mass unit of any atom, which is 1/n, will be that number of n multiplied by 1/n. Let's hope I'm clear here. Let me just go and change PowerPoint because these are panasokonyeza. So what I'm trying to say is, where is Pop? Can you guys see my sharing? So I'm saying, can you see?
Yeah.
Okay.
We
So
can
I'm
see
saying,
yes.
okay, I'm saying 1 in French is called unit. Unit mass atomic. In English, it's called atomic mass unit. If E will be sounds E. So now we're saying 1 atomic mass unit is equivalent to 1/12 of the carbon atom. So we're saying this is a definition of you know what of means, you guys, mathematically? Of means what? Multiplication. Of the carbon 12, of the carbon, teacher chemist, so carbon, of the carbon 12 atom, which will also mean for any atom, for atoms, you take note, for any atom, it will imply that 1 atomic mass unit mass atomique, est égal à 1 sur n of the n. So I'll use maybe, what letter should I use for the mass? I'll use m, small m, for mass of that particular atom. So in other words, what I'm also saying is, give me any element on top 20. What's an element, because you'll be thinking maybe I'm using examples that give me any element. Anyone to shout any element? Just shout any element. Top 20. Calcium. So calcium number 20 with mass 40. So calcium number 20, that's the number of protons, with how many neutrons and protons together? With 20 protons and 20 neutrons, that gives us a mass of 40. So what I'm trying to say is the 1 unit mass atomic of calcium is equals to 1 over, what's the mass for calcium? 40 over the calcium 40, which is equals to what? Maybe I'm confusing you when I say of. This means 1 over 40 times 40. What are you going to get? 1 over 40 times 40 is what?
1.
Exactly, 1. So we are saying they have 40 unit masses. So they have, in other words, so therefore, there are 40 units. And these units make up the mass of the atom. So, in other words, to just conclude, what I mean is there are 1 unit mass atomic, 1 unit mass atomic, 1 unit mass atomic, 1 unit mass atomic. So this is so say so there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36. So it shows that there are exactly 40 units which are equals to the mass of the atom. In other words, what I am trying to imply is when I say 1/40 of the 40 calcium atom, which is equals to 1 unit mass, is this here. So there are 1 to 40 units, and these units are what make up the relative mass of an atom. Is it clear now? I think it's clear. Okay. So there are 40. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So there are exactly 40 units, and these 40 units now, these 40 units make up the mass of the calcium 40 calcium 40 atom. Now, the calcium 40 atom we're talking about here, this one is just the normal calcium that we know. We assume we're going to use the periodic table design. We're going to use periodic table. So it means whenever we are going to start doing calculations, masses will be given here. Masses will be given, and all the things that you need for calculation of relative masses. So what I'm trying to say is 1 unit mass atomic, or bien 1 atomic mass unit, is equals to 1/12 of the carbon atom, which also can be used to say, okay, for any atom or for any atoms that you have, now and you want to calculate the number of units that 1 is equals to, you will say 1 over n over the n mass. Now the n mass for this example was calcium 40. Calcium, there might be calcium 40, calcium 30, calcium 40, calcium 50, calcium 70. It all comes back to the principle of isotopes and every element being an isotope on the periodic table. Yeah. So what I'm trying to say is one unit mass atomic of calcium is 1/40 of the calcium atom, of the calcium 40 atom. Now, what I mean is 1/40 multiplied by 40, that's giving you one mass atomic, 1 unit mass, which also implies, to just simplify, to conclude, it means you have 40 units, and these 40 units make up the mass of the atom. Is it clear? Is it clear? Is it clear?
Yeah, it's clear.
Is it clear for everyone? Mutale, is it clear?
Yes, it is clear.
Okay. Taonga, nani, who's this? Mazina Papa Kole, Mutale, Elisha, Kennedy, Kondwani, Esther, Mumba, Taonga. Is everything clear? If you want me to repeat, I can always repeat. I know someone wants me to repeat, and they're shy. So, Zamba Moche. There's someone that wants me to repeat it. If you're going to take, it's okay. Okay.
Yeah, that's okay.
Everything is okay now. It's clear.
Yes, it's clear.
Okay. So I think that concludes today's school. I guess so. Yeah. So this is the formula I was talking about.
I just have another question, just for behind. Can I ask?
It's not important. So in the next part, we'll be here. The next.
Mr. DM.
Can you guys, just a minute, can you guys see my sharing first? Who is it? Can you see my sharing? Can you see?
Yes.
I want your responses. So we were
Yes.
here. So here,
Yes, we
this
can.
is where we were. This is where we were. Now, this is the formula I was talking about for this one. This part. This part is this is the formula. This is the formula. Then I said, okay, this part is not important for you guys because I'm told you guys that are doing medicine, it's all about to my simple stuff. Sure. But for those that were doing engineering, would have gone in detail how to calculate energy before the mass and liaison. But the idea is you're getting the mass of the noyau and you're subtracting it from the mass that the noyau might possess. Yeah, it's not important. So then you have these. You guys know what this is. It is what you call this. You want that guess this one correct? This one. What do you call this? Okay, I'll start it for you. Is it nuclear fission or nuclear fusion?
Fusion.
Okay. So we all agamba inshallah. So then
My screen can't show anything. Just you keep sharing, but it's not showing anything.
It's Mutale
I
again.
just keep saying, yeah, my network is bad.
No, please wait. No, try to go in your friend's room, like share network. Yeah. Or maybe share a PC. Or maybe you're using your phone. I think because
Yes, I'm using the phone. I'm the only one who's taking class, and the other network is even worse than ours.
bon. No.
Yeah.
I just hope organic chemistry it won't be this way because today's organic chemistry will be fire. So that ends our call for today. So when we get back at is it 15 to 17, we are going to start another history. So today is just history. I'll be discussing to my history what happened about atoms and how the discovery of the what one chance. So today is just quantification of energy. Then we close. So from everything that we've done today, please, are there any questions? I can still go back. There is how many minutes remaining? There's just like 4 minutes remaining. I can still go back. Are there any questions? Elisha, you are the concern, please. What's the question, boss?
Actually, it's done.
It's done. Everything is clear. It's perfect.
Inshallah.
No, I'm saying, no, I'm asking. Is there any questions? Maybe someone wants to contribute.
Boss, I've got a question.
Uh-huh.
Yeah, I was a little bit confused on quantum entanglement and superposition.
I know.
Talk about a little bit.
I know. Oh, this one won't record it. Okay, let me go back to quantum superposition. Let me just look for an image on the internet. Then I'll use that to explain. Because in easy, but you might want to tell my inbox that no quantum superposition. You're even laughing to explain. Okay, quantum. I even saw someone here in the course when I was uploading on YouTube. Someone's name was quantum entanglement. Not bon. You guys should have been attending Nankan. It's interesting when you're doing the engineering stuff. For the engineers, they're enjoying, you know. So, which image? Is everyone there?
Yeah, we're still here.
Okay. So I will share a screen. I was just getting an image that I want you guys to see. Can you guys see?
Oh, yes.
What are you seeing? What's happening?
Is this supposed to be
In the way, Odi?
so, Schrödinger's cat?
Yeah, we're seeing exactly. You're seeing Schrödinger, what you call Schrödinger's cat. So Schrödinger's cat explains the principle of quantum superposition. So we are saying his principle was basically explaining that it was disqualifying Niels Bohr's principle. Or maybe I should give a clue about Niels Bohr then, so that when we come back in the afternoon, I just go. So I'll just give a brief explanation about Niels' principle. So Niels Bohr's principle, he has like 3 postulates, but they also count them as 4. 3, but they are counted as 4 sometimes. The first one states that an atom has got what you call stationary energy levels. The second one explains the principle of energy d'absorption. The third one explains about energy d'emission. And the last one explains the principle of what you call angular momentum. So now, when you come back in the afternoon, I'll go in detail about the same. So now the first postulate is what we're going to look at now. The first postulate states that energy levels are stationary. They are stationary. Now with Erwin Schrödinger's hypothesis, he says the atom has no stationary energy level.
It's 11 o'clock.
Why? Now the question is why? The reason is because the stationary energy levels that this guy, Boyle, said that the energy levels and the stationary thingy was not correct. Now, why? The reason is because of what we call quantum superposition. There's what you call quantum superposition. Now, here is the experiment we're talking about. This is what you call Schrödinger's cat. So I say, take for instance, you have this cat, and you put this cat in a box. Now, you subject this cat to a radiation. Now, the radiation might depend. You might use radium, uranium, you might use neptunium, any radiation that you can use, or maybe radioactive source that you can use. So take, for instance, this is radium. Now, we are saying, I asked you a question, you guys. I asked the question, say, okay, what happens to a cat when you put it in a box and you put a radioactive source? You said it's going to die. Logically, it's going to die. But normally, we assume that, okay, what if the poison or maybe the radiation that we had put there was mislabeled? Take for instance, maybe you as the one carrying out this experiment thinks that this is radium. Maybe it's not even radium. Someone labeled it radium, but what is contained inside is sodium chloride. Sodium chloride does not react with anything. So we are saying, can the cat be alive or dead at the same time? So that's the question we're asking. So it cannot be dead and alive at the same time unless we measure it. We can only find out its state, because you cannot, like I said, even the Bible is the basic principles before the living earth. It defines everything that we're supposed to do. Like, we are not supposed to serve two masters at once. It's the same principle here that we're applying. The cat cannot be in two positions at the same time. Now, the two positions that we're talking about are now what we call quantum superposition. An electron can be found. Now, in quantum superposition, now we are saying an electron can be found in any position, but its position can be defined when we measure the system. So what I'm trying to say is the cat is neither dead, is neither alive. It's in a state of quantum superposition. Now, what quantum superposition simply means is the cat here is not dead. The cat is not alive. It's just there. But now when you uncover the box, you check now, you find that, okay, the cat is dead. Now you're saying, okay, no, the cat is dead. Like, you're now coming to a conclusion saying the cat is dead. Now you'll be like, okay, why did the cat die? The cat died because of the radiation. But still, there is another possibility that the radiation that you were using here might have expired. That's another hypothesis you can come in with. Maybe the radium, neptunium, rhenium that you were using here had expired. Now, because it expired, it didn't work. So now the cat is alive. Now, this just is an explanation of the state of electrons. So Erwin Schrödinger explains to say, Niels Bohr, what you're saying is wrong. What you're saying is wrong. Electrons are not found in stationary energy levels. They are actually found anywhere in the atom. They are found anywhere in the atom. Now, for us to find their position in the atom, we are supposed to measure the system. Now, when we're measuring the system, we assume that, or we take into consideration to know that there is what you call quantum superposition, which is the state of an electron to be in two positions at the same time. So last time I gave an example in organic chemistry. Take, for instance, I know this year we have Deliso Mwanza. We have two Delisos from your intake. We have Deliso Mwanza and I don't know the other Deliso. So there are two of them. So whatever action is done to Deliso Mwanza, for example, say D1, Deliso Mwanza, the one in Sale, I'm told there's one girl, one boy. The boy, whatever action is done to the boy, for example, Kondwan slaps him. Because we are saying an electron is in a state of quantum superposition, when the guy is slapped in Sale, the same action is done to the girl in Cité. Quantum superposition. When we measure what's happening, what I mean by measure is maybe checking. If we check up on the one in Sale or the one in Cité, we say, for example, the one in Cité is eating. Because we know that electrons are always in a state of superposition. What happens to one in Sale is what is happening to the one in Cité. If someone is eating, the Deliso in Cité is eating, it means it's automatic. The one in Cité is eating. It's automatic that the one in Sale is also eating. So that is the principle of quantum superposition. Now, I also come in with another principle that is called quantum entanglement. Now, quantum entanglement is the idea or the principle that explains the effect of an external force on a system. You see? So we are saying two electrons are in a state of quantum superposition. They are in a state of quantum superposition. When one is affected by an effect or by a force, it automatically affects the other one. So if I was to slap the Deliso in Cité, by effect, by the principle of quantum superposition, automatically the Deliso in Sale also has been slapped. It occurs, these states, this quantum superposition and quantum entanglement occur simultaneously. That's the conclusion we can draw. Quantum superposition and quantum entanglement occur simultaneously. Are there any questions, Mr. Kondwani? Or explanation? Are there any questions?
Thank you very much.
Yeah. So if there are no questions on Severa MIDI, Chimie organic, yeah, let's hope you guys did research on nomenclature, because Chimie organic is a bit big. So let's hope you guys did research on nomenclature so that we